All right, folks, we're getting started here in Chapter 4. The beginning of Chapter 4 is primarily going to be a review of exponential functions and logarithmic functions that you learned in college algebra. In Section 4.1, the objectives we'll look at is, what the graph of a general exponential function looks like. Then we're going to look at an application of an exponential decay model. Of course, we'll then look at how to calculate compound interest. And then we're going to define the number e and what's called the exponential function. So here we go. A general exponential function has the form f of x equals a times b to the x. A is going to be a real number, not equal to 0. And b is a real positive number. And b is not equal to 1. In the definition of a general exponential function, you probably remember that the b, that's called the base. It's the base of the exponential function. So let's look at this example. Fill in the table below and sketch a graph of each function. So there you go. There's the table. We have two different exponential functions. 3 to the x is function f, and 1/3 to the x is function g. So get this written down because, I'm going to head off to the chalkboard to work through this, and hopefully we can review some properties of graphs as we're reviewing it. All right, folks, in this example, we were given a table and asked to fill in the table and then to sketch a graph of each function. I actually broke the table into two different pieces. So let's first look at the x and the exponential function f of x equals 3 to the x. So when x is -2, we want to see what f of x is. Well, -2 would come in for x. That gives us 3 to the -2nd, which is 1/3 squared, 1/9. -1, we would have 3 to the -1st, which is 1/3 to the 1st, or just 1/3. 0, so when 0 goes in for x, we have 3 to the 0. Remember, anything to the 0 power is 1. X is 1, we get 3 to the 1st, which is just 3. And then when x is 2, we get 3 squared, which we know is 9. So if I try to plot these points, let's see, I'll make the graph up here. 0, 1, 1, 3, 2, 9, that would be off my board. -1 is 1/3. -2, the y value is 1/9. I would get this as being the graph of f of x equals 3 to the x. So for the function g of x equals 1/3 to the x. Well, x is -2, so that would give us 1/3 to the -2nd power, which is 1 to the -2nd over 3 to the -2nd, or getting rid of those negative exponents, 3 squared over 1 squared, that gives us 9. -1 goes in for x, so we'd have a 1/3 to the -1st. That's 1 to the -1st over 3 to the -1st. Get rid of the negative exponents. It's a 3 to the 1st over 1 to the 1st, which is 3. Then when 0 goes in, well, we have 1/3 to the 0. And we know anything to the 0 power is 1. When 1 goes in for x, we get 1/3 to the 1st power, which is 1/3. And then when 2 goes in for x, we get a 1/3 squared, which is 1/9. So plotting those points, let's see, we have 0, 1, -1, 3, -2, 9, that's way up here somewhere. 1, 1/3, so I'll put that about right here. 2 1/9, and we get a graph that looks something like that. So this is the graph of g of x equals 1/3 to the x power. So we're going to head back to the slides now. Just wanted to give some practice on evaluating an exponential function, looking at the graphs of an exponential function. But we're going to go back to the slides and we're going to kind of generalize some stuff. For example, I know this graph right here represents exponential growth. This represents exponential decay. So that's something we're going to look at when we head back to the slides. All right, let's list some of these properties of general exponential functions. First is the domain. The domain will be all real numbers. The y-intercept is the point 0, 1. Now, if the base of your exponential function is greater than 1, then the exponential function is what we call an exponential growth function. And with exponential growth functions, the limit as x goes to infinity of b to the x is infinity, whereas the limit as x goes to negative infinity of b to the x is equal to 0. And there's what the graph of a general exponential growth function looks like. Just knowing its basic shape is kind of important. So keep in mind, you have an exponential function. The base is greater than 1. You know it's exponential growth. You know what the general shape of the graph is. Now, on the other hand, if the base is between 0 and 1, the function is called exponential decay. And, the limit as x goes to infinity of b to x would be 0. And the limit as x goes to negative infinity of b to the x would be infinity. So here's the graph of a general exponential decay function. So again, recognition is going to be key. You see you have an exponential function. If the base is greater than 1, then you know you have exponential growth. If the base is a number between 0 and 1, then you know you have exponential decay. And it's the general shape of the growth and decay functions that tell you the limits that I have listed here. So let's try an example where all we're going to do in this example is classify the function as being an exponential growth or an exponential decay. So those are the three functions, part A, B, and C. Write them down because I'm going to head off to the chalkboard and discuss them. All right, in this example, we were just asked to classify the function as representing exponential growth or exponential decay. So the first one, f of x equals 1/4 to the x. So the first thing I noticed is that the base of this exponential function is 1/4. And 1/4 is between 0 and 1. Because it's between 0 and 1, I know it's exponential decay. And because it's exponential decay, I know the graph is doing something like that. Part B, f of x equals 2.3 to the x. Well, here the base is 2.3. 2.3 is definitely greater than 1. That means exponential growth. And because it's exponential growth, I know its graph is doing something like that. Part C, f of x equals 0.7 to the x power. Well, here the base is 0.7. Again, 0.7 is between 0 and 1. Because it's between 0 and 1, I know that it's exponential decay, and exponential decay tells me this function, the graph is doing something like that. So being able to identify exponential growth, exponential decay, without having to look at the graph, it's an important skill. So what I'd like you to do is to practice a couple right now. So in section 4.1 exercises, do numbers 14 and 16. Just do part B only. That's the part where we classify it as exponential growth or exponential decay. So you know the drill. Pause the video, do these two, restart the video, and I'll be here at the board working through them. All right, 14 part B is the function f of x equals 4.5 to the x power. Does that represent exponential growth or exponential decay? Well, since the base is 4.5 and 4.5 is greater than 1, this is exponential growth. For 16, the function was 0.22 to the x power. Since the base is 0.22, and that's between 0 and 1, we know this is exponential decay. So why don't we head back to the slide and look at one quick application. All right, after looking at this example, we saw part A here was an exponential decay function. Part B was an exponential growth function, and part C was an exponential decay function. Let's now look at an example where we do an application. So, write this all down. There's the function that models the actual high temperatures in Salt Lake City, Utah for the first week of November 2012. And what we're going to do, in part A, we're going to evaluate and interpret f of 5. And then part B, we're going to just classify the function as growth or decay and describe the behavior of the function as the x values increase. So write down this example, both parts, because I'm gonna head off to the chalkboard and work through it. All right, in this application, this example, it was an application. There were a lot of words. Don't write them all down. You know the drill by now. This was the function that you were given, 59.15 times 0.963 to the x power, and that was modeling the actual high temperatures in Salt Lake City, Utah for the first week of November. And x is the number of days since October 31st. So part A, evaluate and interpret f of 5. So f of 5, well, we put 5 in for the x, and when I use my calculator, I get f of 5 to be about 48.99, or why don't we just round that off to 49? That's going to be 49 degrees. In fact, it's going to be 49 degrees Fahrenheit. So in the interpretation, I would say okay, so that's the number of days since October 31st. So that would make 5 would make this November 5th. So on November 5th, the high temperature in Salt Lake City, Utah was 49 degrees Fahrenheit. Then part B, classify this function as exponential growth or exponential decay. Well, folks, the base is 0.963. That's a number between 0 and 1. That means it's exponential decay, which means it has this shape. So as the x values increase, the function itself is decreasing. That's exponential decay. All right, let's head back to the slides and see what is next. All right, one of the more popular applications of exponential functions involves compound interest. So quick review here. In a prior class, you would have seen the simple interest formula, which is I equals PRT. P is the amount of dollars that's deposited into an account that earns a rate R, and that R is usually, it's entered as a decimal, for T years. When we talk about compound interest, that means you're going to pay interest not only on the principal, the P that was invested, but also on the interest that was previously earned. So if a principal of P dollars is invested in an account earning an annual interest rate of R, again, that's in decimal form, and it's compounded K times per year, then the amount A in the account at the end of T years is given by, well, there's the compound interest formula that I'm sure you remember from college algebra. A equals P times the quantity 1 plus R over K to the KT power. Now, before I go on, there are a couple of items I'd like to point out here. That A, it's also known as future value. P, the principal P, it also is known as present value. And then K, the number of times compounded per year, things to know there. If it says compounded annually, then K would be 1. Compounded quarterly, K would be 4. Compounded monthly, K would be 12, etc. So let's look at this example. Got a deposit of $15,000 was made into an account that yields an annual interest rate of 2.7% that's compounded monthly. So after 8 years, how much is in the account and how much interest was earned? So write this down because I'm going to head off to the chalkboard and work through it. All right, folks, this example, I don't write down all the words, but I will say that a deposit of $15,000 was made into an account. So right now I know in my compound interest formula, I know P is 15,000. It yields an annual interest rate of 2.7%. So I know R is 0.027. Compounded monthly, so I know K is 12. So after 8 years, so T is 8, how much was in the account? And then how much of that was interest earned? So let me mention this again. In the compound interest formula, you could think of P as being the principal. You could also think of it as present value. A, the amount, you can think of it as future value. So the present value, if I have $15,000 today that I'm going to put into this account, the present value of my $15,000 is $15,000. That's presently what it's worth. How much will I have in 8 years? Well, that's in the future. That's why we can think of A as being a future value. So let me just substitute in the numbers. P is 15,000. We said R is 2.7%, so that's 0.027. Compounded monthly, so K is 12. K is 12, and 8 years, so T is 8. So when I fire up my calculator and I evaluate this and I round it to the nearest cent, I get $18,612.02. So that's my future value. That's the amount I will have in the account in 8 years. Now, how much of that was interest? Well, if I put in $15,000 and in 8 years I have $18,612.02, I just subtract off that $15,000 from this amount, and that's how much interest I've earned. So the interest earned is $3,612.02. So just get a little practice here with the compound interest formula. Why don't you try number 36. Let's try part C only. Just 36 part C. So here in section 4.1, go to the exercises, do number 36 part C. After you've done it, come restart the video and I'll be here working through it. So pause the video, do that one, and hopefully you'll get it correct. All right, here in 36 part C, Mrs. Johansson, she's putting $5,000 into an account that yields 6.5% interest. How much will be in the account after 10 years if the interest is compounded weekly? That's part C, compounded weekly. So let's see. She's depositing $5,000, so P is 5,000. The interest rate was 6.5%, so as a decimal, that's 0.065. It's compounded weekly, so K is 52. And she's doing this for, 10 years. So if I crank this through my calculator, I end up with the future value, or the amount in the account in 10 years, as being $9,573.82. All right, so that's it for this compound interest problem. Let's head on back to the slides and see what is next. All right, now it's time that we look at a very famous irrational number, and that number is E. And this is technically how E is defined. E equals the limit as k goes to infinity of the 1 plus 1 over k raised to the k power. That is the definition for E. Just like with pi, pi is probably the most famous irrational number. Pi is defined, or pi actually equals the circumference of a circle divided by the diameter. We also know there's a decimal approximation for pi, and and here in a minute we'll look at the decimal approximation for E. But before we do that, this thing called the exponential function, so like the main exponential function, has the form f of x equals a times e to the bx, where a and b are both real numbers. So this is the most important form of an exponential function, where the base is e. Now, e as a decimal, it's approximately 2.71828, and it continues on forever and ever, just like pi. That's what it means to be irrational. But it's a positive number. I mean, it's greater than 1. So e is greater than 1. So that means the graph of f of x equals a e to the bx, it's going to depend on whether the value of b is positive or negative. So if b is greater than 0, we're going to have exponential growth. If b is less than 0, we're going to have exponential decay. So, again, the pictures. So for the exponential function, f of x equals a e to the bx, that's the exponent. If b is positive, you have exponential growth. If b is negative, you have exponential decay. So just kind of file that away. It's something you might remember from college algebra, but it's going to be very beneficial going forward. All right, so now as k approaches infinity, so it gets incredibly large, we go back to the compound interest formula, and that compound interest formula turns into the continuous compound interest formula, which is a equals PE to the RT. A is still the amount, P is still the principal, R is still the interest rate as a decimal, T is still time in years. A could still be called the future value, P could still be called the present value. But this is the compound interest formula we would use if we are told our interest is compounded continuously. So let's check out a quick example. A deposit of $15,000 was made into an account that yields an annual interest rate of 2.7% compounded continuously. How much is in the account after 8 years? Now you may notice this is the same example that we just did. The same deposit, the same interest rate. The only thing that has changed is the compounding. I think in the previous example, the compounding was done monthly. So here in this example, we're going to do the compounding as if it were being done continuously. So make sure you have this written down, because I'm going to head off to the chalkboard and work through this one. All right, in this example, it was $15,000, interest rate of 2.7%, compounded continuously. How much is in the account after 8 years? So we're going to do this and we'll compare it to the prior example that we did. But before we do, I want to make one quick comment off to the side. If we know P and we know R, so if we know the present value and we know the interest rate, we can represent the compound interest formula, we can write it as a function of T. In other words, it would look something like this. So that, if we know what P is and we know what R is, so for this problem, just for example, P is 15,000 and R is 0.027, and we just leave the independent variable as T, I could call that the compound interest function. And then it could tell us for different time intervals, for different periods of time, how much or what the future value would be, how much would be in the account. So if I put 20 in for T, A of 20, that would tell me what's in the account in 20 years. So that's just a quick little aside. For this problem, well, we know what P is. It's 15,000. R is 0.027. T is 8. When I fire up my calculator, I get $18,616.54. Now compare this to the last example we did. It was the same amount of money, the same interest rate, but it was compounded monthly. And I think there we saw the future value was $18,612.02. This is a little bit more because it's compounded continuously, but it's like $4.52 more over that 8-year period of time. It's kind of interesting to look at. So just to practice this, I would like you to do number 52 in section 4.1. And I believe in number 52, it's going to talk about the compound interest function. So that's why I kind of mentioned that, before I started this example. So pause the video, do number 52, restart the video, and we'll make sure that you have it correct. Okay, number 52, it says $800 is invested at 4.75% interest rate, and this is it's compounded continuously. See, the direction said use the continuous compound interest function to evaluate A of 7 and interpret. So A of 7, you're going to end up putting 7 in for T, so it's like 7 years. But as I was saying before the last example, your continuous compound interest formula, if you know R and you know T, if you know P and you know R, you can write it as a function of T. So here we know what P is. We know P is 800. We know R is 4.75%. Whoops. I'll just write that as T. So that's really for this problem what the continuous compound interest function would look like. It's no different than what we did before. So when it says evaluate A of 7 and interpret, that's just the final bit of information. You're being told T has a value of 7 for 7 years. So this problem could be reworded as $800 is invested at 4.75% interest compounded continuously. How much is in the account in 7 years? That's what we're doing here. And so if we evaluate the function at 7, let's see, when I use my calculator, I get $1,115.56. So that means the future value or the amount in the account after 7 years is $1,115 $1.56. So folks, that's it. This section was basically calculus free. It was just a review of exponential functions that you would have seen in college algebra. So now you can do the homework in section 4.1. So do all the exercises in 4.1. Thanks for watching.